about multi-object systems, and there's a particular way, an extremely useful way to analyze problems that have more than one body. The limitation for this is that they have to have the same acceleration. So they have to be connected in some way that they accelerate at the same rate. So let's go through, there's two problems in this set. The first one is looking at this situation here. She's pushing to the right on block A, which is touching block B, which is touching block C. And we're going to go through a series of free body diagrams for blocks A, B, and C, and then for each, and then we'll do it for the entire system, and we'll break things up. So let's do this. So we're going to do A, B, and C. And so we've got force of gravity on A, the normal force on A from the floor, and we'll call this the force of the push. Okay? And then there would be friction between A and the floor. For B, we've got the normal force from the floor, we've got the weight of B, we've got the normal force from A on B, and we've got the force of C, it's a normal force of C on B, and we also forgot that B is touching A here. I forgot. Oh, it says ignoring friction. Let's get rid of that. Actually, there we go. A little bit better. This is going to be the force of, the normal force of B on A. Okay, and then the third one, for C, we have the gravitational force of C, normal force from the ground. We have the force of B on C, and there's nothing on this side pushing back. So what are our action-reaction force pairs here? So this is D. So let's look up here. We've got this one, B on A, and A on B. So that's one action-reaction force pair. Here we've got C on B and B on C. That's it. There are no other action-reaction force pairs here. That doesn't mean there are no equal forces that are pointing in opposite directions. Normal and weight are equal and opposite, but they're not action-reaction force pairs or third law pairs. Okay, for the whole system, if we draw it like that, A, B, and C all together, you're going to end up with forces. You're going to have weight of all. You're going to have the normal force on all. You're going to have the person's push on A. Any of these action-reaction force pairs, they cancel out because they are internal, so you leave them off. And that's it. Then if we do A and B, and B and C, you end up with force AB of gravity, normal force from the floor. We've got acting on B, we've got force, normal force of C on B, and then we've got the force of the person's push. If you're looking at just this one, it's the force of gravity of BC. We've got the normal force of B and C, BC, the floor acting on them. You've got what's here, A, the force of A on B, and that's it. So now what are your action-reaction force pairs? Well, you should, we don't have the two different systems here, but this, B on C, right, this is the same. So the action-reaction force pair here goes with this one, right? You would have to have C as the other object. And if you're looking at BC, then you would look at this. This is the action, A on B, it's B on A. So those are your action-reaction force pairs. Why is the choice of system important in the problem-solving process? Right, it allows you to ignore internal, what you're determining to be internal forces. And hopefully you see that this whole idea of what's internal versus what's external is very subjective. So choosing the system is a strategy. So you will get the same exact answer if you use these three separate or together, but it depends on what information you're being given and you have to solve for. Listen, if I want you to solve for the force of B on C, well, you have to break it up. But if I want you to solve for the force of the, the force of the push, well, you can use this, and that would be easier. So like those are the things that you can do. The masses are this, this, and this respectively, and you were given this force, what's the acceleration? So let's do it with the whole thing as the system. So we're going to use the free body diagram from B and writing out Newton's second law in the direction of motion there, or in the direction of acceleration. You have force of the push equals, and this is the total system mass. So it's A plus B plus C times A. So when you when you do use the whole thing as a system, make sure you use the total mass of the system. So this is 200. This is 10 plus 5 plus 20. And this is A, so that's 35. So whatever 200 divided by 35 is 5.71 meters per second squared. Okay? Okay, problem number 2. So we have 3 boxes here. One's on the table, 2 are hanging. It's sort of like the lab we had, as if we had just like one side of that. Define the entire system and draw all external forces. So I'm going to show that this whole thing is the system. So I'm going to make this my line of action. The line of action is completely arbitrary. Let's identify the forces. Weight of 1, weight acting on 3, weight acting on 2, those are all external. The normal force of the table. And that's it, because any tension forces, those are internal, so we don't need to do that. So we did that, and we did that. So define the system as individual objects. So here's 1, we would have tension and weight 1. This one would have Ft, let's call this Ft1, Fg2, Fn table, and this would be Ft3. We call it 3 on 2, 1 on 2. This is 2 on 1. And then this one has Fg3, Ft2 on 3. Okay? And for each of these, you would have, your axis would be vertical, horizontal would be your line of action, and down would be your line of action. Action-reaction force pairs in this case, hopefully you could hear this, and this is an action-reaction force pair, and this is an action-reaction force pair. Okay, so let's write a single expression for acceleration of the system. So to do that, I'm going to do this. You could do it here, but it's a lot more work, so I'm just going to do it here. So I need to, if I'm going to write Newton's second law for my line of action, then I'm going to write what forces are along the line of action. Well, this one's in the positive direction. This one's in the negative direction. These two are perpendicular to the line of action, so they don't affect the line of action. And then you have to do the total system mass times acceleration. So you have m3g minus m1g over m1 plus m2 plus m3. So now this is kind of useful for making predictions. When m3 goes down, so here's m3. When m3 decreases, what happens? Well, this term goes down a lot because multiplied by 10. This term goes down a little. So this is going to be 10 times bigger than that. So we're mostly going to pay attention here. The numerator decreases, so acceleration goes down. And that should make some sense. Listen, if your mass here that's pulling down gets smaller, it's not going to pull down as much, period. Okay? And then for the last one, what if we don't ignore friction? What's going to happen? Well, where would friction play a part? Well, friction would add in right here, opposite the direction of motion, which would mean that now my expression changes to mg3 minus fg1 minus friction. So let me just write this. Friction here. So you'll notice the equation seems pretty much the same except for this additional term. And what's that term? What does that term do? This term, friction, makes the numerator smaller. And when the numerator gets smaller, then acceleration goes down.